Okay, so you should now have downloaded the moons and planets Excel files from GitHub, from the GitHub data folder in our repository, and then save them to the a data folder that is at the same level as your lessons folder that you're in now that allows these relative paths to work. So we're going to read in the Excel files as data frames. We're going to merge them, left on planet name, right on planet name. We're going to add columns for volume. So we're going to use 4/3 pi times the radius cubed, and then we can look at that. And of course I didn't do it again, so copy the okay. So now we have this nice data frame of all this information about the moons, and we calculated these extra columns. And so let's say we want to see what's the Pearson correlation. This is like a linear regression. So on the values of the diameters. So we can do a SciPy. So this function is SciPy.stats.PearsonR. If we want to, remember we can type A, that will add a column above. We can learn about this function. Calculates a Pearson correlation coefficient and the p-value for testing non-correlation. And I can just make this, I can just kind of hide this code by converting it to a raw NB convert, so when I execute the whole notebook later on, it won't generate that help. It's just kind of sitting there. Okay, so I'm going to run a Pearson correlation on the planet's diameter and the moon diameter. And then I'm going to store that R value and that P value. So this is the correlation and then the P value. So they're loosely correlated, the diameters are. And then if we run the correlation on the volumes, so now we're running it on the volumes, you can see there's a stronger correlation, and it's now significant with P less than 0.05. So this kind of makes sense that the volumes might be more correlated to each other than the radii, or than the diameters. We can also do a rank-based correlation. So this is a Spearman correlation. Again, we can do use that question mark to pull up the doc string that'll tell us about this test and how to use it, and maybe even sometimes, yeah, it gives us an example. So super handy thing to have at your disposal. Even if you're not connected to the internet, you can learn about this function. So we can do a rank-based regression, and we see that there is a correlation, and it's significant between the diameters and the volumes, both. And actually, the correlation is the same because as we rank them, the rankings don't change. You're just amplifying the range, right? So, and again, we can plot the linear regressions using Seaborn, and we can see that there is a correlation that's moderate in both of these cases, but seems like there's something that we're still not capturing here. So for example, you guys know this from the homework that this one here has quite a large moon diameter relative to the planet diameter is the Earth's moon. And the pattern is even more dramatic in the volume. So it's maybe not obvious immediately, but this is the Earth's moon, and the planet volume on this scale is almost 0, whereas the moon volume is still quite large. So what if we look at the ratio of moon size to planet size and see what happens there? So we can generate this relative diameter or relative volume column. So we've added a new column, and we can now plot those values here. So if we plot relative diameter versus moon diameter, or relative volume versus moon volume, so this is the volume of the moon relative to its host planet, or the diameter of the moon relative to its host planet, you can see that the Earth's moon, which is this one up here and this one here, is really an outlier. So we can test that in different ways. One thing we can do is we can plot the same value, or the same data, as a distribution plot, so a seaborne dist plot, and we can see that the moon relative diameter is sort of centered around 0.02, but the Earth's moon is way up here, and with volume it's even more dramatic. All of the moons in the solar system are down here except for the Earth's moon, which is way over here. We can in fact, if we make that other one a log plot, you get kind of weird looking histogram, but you can see with the, so we might want to turn the histogram off, but you can see that there's this, all these other moons are down here, and the Earth's moon is up here. So let's say we want to test that the moon is an outlier. So this is why we installed this outlier utils. So this is called Grubb's test for outliers, and if assuming normally distributed univariate data, you can detect and look at outliers, or you can also remove outliers for further downstream analysis. So here, first we're going to print the outliers from the data set of relative diameter. So this is, since we imported the Grubb's test as Grubbs, we can do Grubbs, and then this has a function called max test outliers. So we can look at the moon relative diameter with an alpha of 0.05. So the alpha is the p-value cutoff. So this generates an error because this package isn't using the latest Pandas version, but we won't worry about that for today. So the outlier that we get is just this one here, which corresponds to the moon's relative diameter. So the moon has a diameter relative to the Earth's diameter of 0.27. And if we look at, if instead we want to remove outliers and just get what's left, we can do a Grubbs, basic Grubbs.test, which will again take an alpha, but instead it's going to generate the list of values without the outlier in it. Same thing with volume. We can take this DF solar planet relative volume with an alpha. This time we have to actually crank up the alpha really high because by volume it's such a strong outlier. So the relative volume of the moon to the Earth is about 2%, but for all the other moons in the solar system it's much lower. The highest one is about 1/100th of that value. So pretty fascinating astronomy, and also a really nice tool to be able to deal with outliers.